Yes. Hello, everyone. I'm Haoping, a PhD student from University of Toronto. Today, I would like to talk about our paper, Seeing Glass, Joint Point Cloud and Depth Completion for Transparent Objects. Transparent objects are commonly seen in kitchen, lab, and industrial scenes. All of them have the potential to be manipulated by robots. One particular use case we are interested about is automating the chemistry lab. Existing methods like this robot arm from Professor Andy Cooper's group can already perform material discovery experiment using Bayesian optimization. Yet they mainly relies on position-based control to manipulate transparent glasswares as vision system cannot handle them reliably. Why, you may ask? Unlike humans who can easily detect and locate transparent objects in a picture, RGB sensors see a scene like this differently. When comparing the raw depth from the sensor with the ground truth depths, the transparent objects are almost completely invisible in the sensor's view. The difference is more significant if we deproject the depths into a point cloud. This difference is mainly due to the transparency nature of the glassware as well as the highly reflective surface. Existing methods like ClearGrasp and LIDF takes the RGBD image as the input and train a network using a synthetic dataset to aim to fix this problem and predict the whole scene steps. Additional methods like LIT and key pose use only the RGB images and predict the object depths using a model-based approach. That is saying you have to know the object's CAD models in order to do the predictions. To recover transparent object depths, we propose TranspareNet, a novel joint point cloud and depth completion pipeline taking the RGBD image as well as the object mass as the input. In the pipeline, the point cloud completion network firstly generate a sparse depth prior, and then the depth completion module takes the sparse prior RGB image and object mask to predict the final object depths. With our joint pipeline, one goal is that the distorted transparent object depths discarded by existing methods can be effectively utilized via our point cloud completion modules and can be used to guide the generation of the sparse depths prior, which can be used later on for the depth completion module. Well, when we compare it with ClearGrasp, choose to mask out the transparent object depths showing on the right. TranspareNet can recreate the object depths with high accuracy, and when compared to existing methods, it outperforms the state-of-art LIDF on ClearGrasp dataset. To train our pipeline, transparent object datasets are needed, yet existing datasets have their limitations. For example, some datasets have limited real image collections, for example, ClearGrasp, and others lack of the depth informations, and many only includes empty objects, whereas in real life, filled glassware are commonly seen. And finally, most of them are collected in a slow manual creation method. Because of that, we'll create our own data set with sufficient size, close to real objects filled with different contents. And most importantly, if we propose a fast automated creation pipeline, which allows swift expansion of the data set to include additional objects. Currently, our data sets have 6 different objects. Each of them may contain 6 colors of liquid as content, and they are placed in 4 different backgrounds. For our dataset creation process, with the eye-in-hand RGB camera mounted on the robot and a APROTAG-based annotation method, we gain about 10 times speed up compared to ClearGrasp methods. And also, we reduced the human interaction requirement by around 2,000 times. Currently, each image takes around 3 seconds to be collected and annotated, and human interaction is only required once every around 500 images. The eye-in-hand camera can scan the scene from various viewing angles and distance automatically by carrying by the robotic arm. And for each image captured, the object poles are derived from AFROTAG poles, and a virtual scene is created by placing the CAD model to the corresponding object locations. With the recreated scene, annotations including instant segmentation mask, ground truth steps, and object poles are generated and recorded. Additionally, our automated creation pipeline can quickly gather other datasets to expand the scope. For example, we add 2 additional objects to our datasets with around 4,000 images using less than 4 hours. This allows the community members to tailor the dataset according to their applications by including the targeted objects. With the dataset, we train our point cloud and depth completion modules separately. Let's first look at our point cloud completion network. For this part, we reframe the depth estimation problem into a point cloud completion problem. To do that, we first isolate both raw and ground truth depths for each individual objects and deproject them into incomplete and complete point cloud pair, and then use the pairs to train the point cloud completion network. And the network's output is being projected back to the depth space and then merge with the raw depths to create the sparse prior. The point cloud deprojected from the depths differs a lot from common point cloud datasets like ShapeNet, where our point cloud completion module is pre-trained on. Because of that, it needs to be pre-processed in order to maintain the point cloud completion module's performance. Namely, we do a recenter and rescale process before feed it to the network. For our point cloud completion network, firstly, the incomplete point cloud is voxelized into a 3D grid where each cell's corner weight is sampled from the points lying inside a cell. And the half-fill grid is populated using a 3D CNN network. And a coarse point cloud is sampled from the filled grid by sampling the points inside each cell using its corner weights. Finally, a MLP takes the coarse point cloud as well as the populated grid features to do a final refinement and predict the completed point cloud. To evaluate the point cloud completion network's performance, we deproject the depths. We project the depths back to project the point cloud back to depths and evaluate it using the following 3 metrics: root mean square error, mean absolute error, and absolute relative difference. Point cloud completion module alone can recover depths with high accuracy from the raw sensor reported depths. When we only consider the non-zero depths reported by the network, its accuracy even outperforms our combined transparent net pipeline. Yet, due to the 3D CNN low resolution, the network's predicted depth is very sparse with many missing depth areas shown here. Because of that, the sparse depths overall performance is considerably worse and cannot be used directly, so we treat it as a prior for the depth completion module. Now let's look at our depth completion parts. Our depth completion module takes the sparse depths from the point cloud completion module and the RGB image and use them as the input for a refinement-based encoder-decoder network. And we use a decoder modulation branch and take the mask as the branch input. This is aimed to focus the network attention to complete the depths only within the transparent object regions. And finally, we will output the final depths. Our depth completion module alone, trained on Cleargrass dataset, outperforms Cleargrass and LIDF, which is the current state of art on the Cleargrass dataset. And when we combine the point cloud and depth completion module together to form the transparent net pipeline. We find for the network trained on our own data set, it outperforms both ClearGrass and our aforementioned depth completion module alone in all three types of scenes, including from 1 to 3 transparent objects. Here are 3 examples from our test set. The red brackets showing in the figures show the regions where TransparentNet outperformed the depth completion module alone. Overall, we find that TransparentNet has a better performance for closed up and occluded objects. However, our methods still have a hard time in certain complex scenes. Here are 3 examples we find. Mainly, the scenes are the filling cases are associated with highly overlapped objects. In summary, transparent object depth estimation is a challenging task, requires ongoing research. In order to solve this problem, we propose an automated dataset creation pipeline and collected a dataset with 15,000 images with the potential to scale up to additional objects quickly. And finally, we proposed TransparentNet, a joint point cloud and depth completion module, which is the new state of art on ClearGrass dataset. And finally, I want to thank my co-author, Iru and help from Sagi Apple and my advisor, Alan Astru, and Iru's advisor, Animatch and Flory.
Presentation.
Thank you, Haoping.
Any questions here? Having a look at the chat. Yeah, so I might have a question. How much does your approach depend on the shapes of the training data set? So how would you extend that to maybe different kind of objects that are not in the training data, especially the depth completion, right? I guess that depends a lot on the shapes of the object that you have.
Yes. Currently, our dataset is mainly focused on the glass wheels commonly seen in the lab. So I would say it's kind of semi-focused on that. But when we test it on the ClearGrass dataset, which include additional objects, for example, like a transparent heart, it still performs relatively well. I would say it's not very dependent on the object shape. And additionally, if you are mainly working on objects that is not close to a container, you can always use our pipeline to expand the data set.
Okay, thank you. There's one question here.
Hi, so how would your network deal with non-transparent objects? Because I guess in reality you would have both transparent and non-transparent objects.
For the non-transparent objects, we will basically doesn't do any completion on their depths, because the depth sensor alone can obtain a good enough depth for the for non-transparent objects. So it basically will be masked out.
And you've done some tests on this, or?
We haven't do any test on like a mixing with like transparent and non-transparent objects yet. Yeah, sorry for that.
Yeah, thanks.
Okay. Are there any questions from the chat, Rudolf? Is she still there? I don't see any. Okay, in that case, let's thank the speaker again. The next speaker